Good afternoon, everyone, and welcome to day 3 of the COSI Science Festival. The second year we're doing the Science Festival. This is our digital version. We call it the Coronavirus-Induced Digital STEM Immersion. We call it the COSI Science Festival. We have some incredible guests during the Science Festival, people who've stopped their daily work and decided we want to be part of this digital STEM infusion. And with that, I couldn't be more excited to welcome the United States Department of Energy Undersecretary, Mr. Paul Dabbar. Mr. Dabbar, before you jump in here, I want to let the fans know that this is your second time you're visiting COSI. The first time you came here in Central Ohio, you met with a lot of our civic and business leaders talking about the energy field and the energy sector and how Ohio can play a critical role in that nationally. So I thank you for coming then. And today I thank you for coming back to be part of our extraordinary Science Festival. Governor DeWine calls it the largest science event in the history of Ohio. So welcome aboard. Thank you for being here.
No, it's great to be here. I mean, Ohio is really the center of a lot of things that we work on. Just in the Columbus area, obviously, a lot of the transportation and the city topics. Big energy companies are headquartered in Columbus. Our engagement with you all, with Ohio State. And a lot of the hospital systems, both north and south in the state, and then Battelle Labs being in Columbus. It's a great center for science, and it's great to be engaged with you again here.
Well, again, thanks so much. And actually, that's a great place for us to start. So, of course, this is all about science, technology, engineering, and math, and promoting that, not just Ohio, but throughout the nation. And you mentioned Battelle. Battelle is one of the national labs. For the audience out there, and you have adults and you have kids listening right now, talk about how many labs do we have, and what does it mean to be a national lab? And then if you can contextualize a little bit more about our great jewel right here, Battelle, that'll be great.
Yeah, so the DOE runs the National Lab Complex for the country, which really came from the Manhattan Project. A lot of people don't realize that DOE, the predecessor for DOE, was the Manhattan Project. So the national labs that were stood up as part of the Manhattan Project, which was an idea of Albert Einstein. Albert Einstein wrote a letter to FDR in 1939, pointing out that scientists in Germany were working on in the area of physics and could become up with a weapon, and that the U.S. government should do something about it. And so that letter from Albert Einstein stood up the Manhattan Project, and the 3 original national labs came out of that. So that was Oak Ridge, Hanford, and Los Alamos, and that's where Oppenheimer and the others did all their work. And then at the end of the war, it was decided that Vannevar Bush, who was running the technology area for the country for World War II, said that we should take these wonderful people who were there for that national project and to expand it to broad-based sciences. So those 3 national labs have now expanded into 17. There are 60,000 people who work at the 17 national labs.
Wow!
It's the largest basic research organization in the world. It's the largest generator of Nobel Prizes in the world, primarily in physics and in chemistry.
Wow.
So that's what I have an opportunity to work with every single day, and that's a large part of the core of DOE are the 1,000 people and the 17 national labs.
17 national labs, do they collaborate on projects, or are each of them mandated to work in a specific field? And for the younger kids out there, how can they aspire to be one of those scientists or engineers that actually gets to graduate and be part of the national labs?
Yeah, so it's the 17 national labs that we run with our partners, including Battelle. It's a little bit like a university system, right? It's like the UC system in California or the SUNY system in New York. And so it's basically just a number of different campuses, effectively with the president of each campus. We call them lab directors, but it's not much different. And the big difference between a university and a national lab is that at a typical research university, like Ohio State or others, you might see half of the effort doing research in medicine or chemistry or so on, and the other half in teaching, give or take, right?
Sure.
MIT, same, and so on. The DOE National Lab is like 100% research university. And so there's a lot of similarities to these national labs to a lot of the university system, and but the difference, one of the differences is that the U.S. taxpayer, the American citizen, funds us, and we go build facilities that researchers from Ohio or Florida or Alaska or any place or internationally can come and use based on merit-based transnational free access if they publish. And so university students all over the country come up with ideas to use supercomputing capacity, imaging, colliders that we build. And if they have the best pitch, right, the best proposal, they can come. And so you could be going to school any place, any university, part of a research team. You could be an undergrad, you could be a grad student, you could be a professor. And if you come up with an idea that said, if I had access to this, to this at Oak Ridge or at Los Alamos to do this research, we'll give it to you for free, effectively, as long as you publish. So if you're so that's how students, you can think about, you could be any. The other one is we have researchers who work for us, right? It's not just about the facilities. And so if people who are interested in a full-time career in research, in particle physics, in biology, computational biology, in chemistry, and you want your full career doing research, we have 60,000 people we hire. And it's absolutely a career path. If discovery science and wondering how the world works, that's and you can do that at universities, but we do it for the full footprint.
Now that's fantastic, folks. You're listening to Undersecretary Paul Dabbar, runs the U.S. Department of Energy. This is COSI's second science festival, called the COSI Science Festival. Because of coronavirus, we're bringing it to you digitally. So, Undersecretary, you talked about the origins of the labs, the national labs, and you mentioned Albert Einstein, 1939, helped catalyze it, opened 3 labs, and the big one, of course, Los Alamos, and that project, that Manhattan Project, that definitively changed the 20th century for us. An amazing, unbelievable project. You're overseeing now the entire Department of Energy, all 17 labs, plus you do a bunch of other stuff. What's as exciting for you right now that kind of elevates to the level of the Manhattan Project? What's the big thing that really gets you excited about that the Department of Energy oversees?
Well, let me hit on 2, one very practical and one very discovery science. From a practical point of view, looking at quantum information technologies that are different, extremely different than digital technologies today. We're right at the cusp of taking ideas that were generated about physics from Niels Bohr a little over 100 years ago. It is really, people could look this up, very entertaining arguments between Niels Bohr and Albert Einstein about the physics of the small, which is quantum, and the physics of the large, right, which Einstein and general relativity and other of his series, and Niels Bohr had identified that you could impart information into a photon of light or into an ion, an atom. You can program the data into an atom. And we've now just reached the point at which we can actually create devices to actually isolate a photon or isolate an atom and program the data into it rather than a transistor, which is a 1 or a 0.
So I think for the audience, I think it's important to break that down a little bit. So we're talking about right now, your typical computer, your cell phone, all digital technologies is what's called binary. It's either storing information, whether it's your PowerPoint or your essay on Word, it stores the information either as a 1 or as a 0. But now you're talking about we're exploring quantum, which allows us to have, I think, like almost an infinite number of places to store information. Is that correct?
That is correct, because instead of a 1 or a 0, if you think about a sphere, and at the top is a 1 and there's a bottom of a 0, a transistor can only do the 1 or a 0, right? It's only on or off.
Yeah.
And what you could do with programming a piece of data, for example, into an ion or into is that if you think about the sphere, it's a vector. Like how many different arrows can you draw from the middle of the sphere to someplace on the sphere?
Sure.
It's, as you said, infinite, right? How many different arrows that you could draw from the center of the sphere to someplace on the outside?
Yeah.
And so, in theory, you could have you could program an infinite amount of different types of information into one atom. The reality is, you're trying to. It's hard to program and control that. So we can get a lot of different ones, and we're now at the point with the technology that we could program a piece of data into that sphere, so to speak, and we could come up with incredibly large amounts of data that we can store in 1 qubit rather than just a 1 or a 0. And so quantum computers, quantum internet, these are things that we're working on here today. And young kids, this is an area that does not exist really at universities. It's just beginning.
Yeah.
So new fields are being stood up. So if you want to, if you're interested in saying what's really the new thing that's coming up, this is a hot area because of where we are with a lot of this hardware being developed now.
That's fantastic. So 2 things, audience. One, if I'm not mistaken, this will allow us to store a lot more information in much smaller spaces, and it'll also allow us to process things much faster. Is that correct?
Absolutely. The numbers are, I can give an example, but it's monumentally different than the top end computers that we have today. That's the possibility in the next, call it 5 to 10 years, where we can do. So that's applied area of science. I could give you the second one, which is quite a bit different, which is discovery science. It's really wondering how the universe works. So there's an area that we cover called a high energy physics. High energy physics, we take a look at how the universe works. And understanding how the universe works. So the core of this is, when you're like 5 years old and you walked out at night and you looked up into the sky and you saw all the stars and everything that made up, and you kind of wondered, how does that work? How did we come to be? Right? Those kind of really, really early thoughts of you, and kind of, asking the early questions of science. Everyone kind of had that moment, right? Of looking up in the sky and wondering. Well, the area of high energy physics is really how the universe came to be. And we have a number of major steps and things that were going on. So I'll give you a couple of them. When the Big Bang happened, the general theory is of around quantum fluctuations and how did something come from nothing. Is that why didn't equal amounts of matter and antimatter get created? Because that's what a lot of the early physics theories would lay it out to be. And then if equal amounts of matter and antimatter were created at the Big Bang, why are we even here? Because they would have collapsed on each other and turned back to energy, and there would be no matter.
Sure.
So that's a big problem and a big question. So there's something called CP symmetry or CP asymmetry, which is charge symmetry or asymmetry. And that means is maybe when the universe was created, that there was a reason why there was more matter than antimatter, rather than it being equal. And so we have a whole series of research on how particles get created. We can actually create particles many different ways and see if matter and antimatter are not being formed at equal rates with those reactions. Or maybe we actually create antimatter hydrogen on a regular basis
Mhm.
at one of our facilities.
Mhm.
And so we're doing work on does anti-hydrogen operate any differently than regular hydrogen? And so there's researchers who are doing work on that. And the one thing I like to say about that piece of research, which I find is entertaining, they were talking to me about generating anti-hydrogen and doing research, and they were explaining it and going through it, and they were so excited, right, about what they were doing. I looked at them because we fund them, I looked at them and I said, I bet that if we didn't pay you, you would still be doing it. They go, oh yeah, of course. We're not going to admit that too much, but yes, you're right.
That's fantastic. Listen, you're listening to the COSI Science Festival, Digital Edition Year 2. We have none other than Paul Dabbar, who is the Undersecretary and heads up the Department of Energy. You just heard him espouse how he and his great scientific and research team are smashing particles together through accelerators to discover new particles and find out if antioxygen is as powerful as the oxygen. I mean, that's just incredible. I want to say, just before, we actually had the pleasure of having one of your colleagues on, none other than lead administrator of NASA, Jim Bridenstine, and he was talking about, you know, the probability, which we all know with all of these celestial objects out there that are orbiting suns or stars like our sun, and obviously the probability of possibly having life, and that kind of exploration to discover life out there, considering you guys are talking about the origins of life.
Yeah. So there's one piece of science that Jim Bridenstine, Administrator Bridenstine, and us work on together with different facilities. They have some in space. We have one at the South Pole, which I just came back from in December. Okay. And it is to map something called the cosmic microwave background. Mm-hmm. So NASA has a telescope up in space that maps the cosmic microwave background, and we have one at South Pole because it's a very hard place, but there's advantages to having it down there and on the Earth. And both of us work together to map what the universe looked like from time zero to time 350,000 years after the Big Bang. Okay. And what's exciting about it is that light itself couldn't escape during that time frame because it was basically the universe was a big plasma ball. Mm-hmm. So we figured out a way to actually map what the universe looked like when it was basically just a small plasma ball, and how gravity started coming together and creating clumps that the galaxies. And so NASA has a telescope that's looking back to right after the Big Bang, and we have a telescope that also does the same thing. And we work together on mapping the universe immediately after the Big Bang. It's really exciting stuff as just one example that we do with NASA.
That is incredible. Rand McNally, I love old school maps. Rand McNally would be so proud to see where mapping has actually come in the 21st century. That's really cool. We're actually getting a bunch of questions from our Twitter feed here. I'm going to look over on the right. So one question, and I know a little bit about your background, so I really love this question. How did your background get you to be the Undersecretary and head of the Department of Energy? So you got, again, a lot of adults out there, but you also have some young kids. So if you don't mind sharing just a little bit, walk through your bio to show the audience that there's so many possibilities with your kind of background.
Yeah. So I'll step through that, but I think the most important thing I'd like to recommend to students, to children, is always be open to the idea that comes in front of you. And luck is just a confluence of preparedness and opportunity. And that's certainly a good example of my life, but I think this is a good example of most people's lives.
And that's great. You just reframed one of my favorite quotes from Louis Pasteur: "Chance favors the prepared mind." So
there we go. Very
interesting.
So from my point of view, I studied nuclear physics and engineering. When I was in 5th grade, I decided I wanted to do something in the military, and I said I wanted to go do nuclear submarines. Okay. And go to the Naval Academy, and strangely, it actually happened exactly as you thought about. I thought about it in 5th grade, okay. And so I studied nuclear engineering and physics. As a part of that, it was a lot of computing, as you do modeling associated with that. I went to go work at a lab, applied physics lab at Johns Hopkins. I dealt a lot with computer modeling. And then I went off and ran a reactor in a submarine. So had real life, engineering experience when I was young, of being in charge of a nuclear reactor in a submarine and liberating neutrons for a living and boiling water, so to speak.
You got to say more than that, because you just said I ran a nuclear reactor like you went for a jog, and now you're talking about boiling neutrons. So share a little bit more. What does it mean to run a nuclear reactor for the layperson?
Yeah, so submarines in the United States, in order to be able to stay underwater for literally until you run out of food, so you can about 3 months, is that you have a reactor that can generate energy for 10 plus years with one fuel load. Wow. And so you build a nuclear reactor, you have uranium fuel, and you have all the equipment around the generation of neutrons, which causes the nuclear reaction and heats up the fuel. That's all it does. The nuclear fuel is heated up. It heats up the water, very, very hot, and you take that water to make steam to run turbines. Got it. And it was invented effectively by Admiral Rickover right after the Manhattan Project. He said, "Hey, we could take nuclear power and use it to make energy with." And as a predecessor of DOE, that's one of the major accomplishments of the history of the program. And so I did that because I went to the military and was an officer, and ended up doing that and traveled around the world, including going to the North Pole on my submarine, where we did both defense work as well as setting up environmental monitoring stations. A lot of the early monitoring of the environment in the Arctic setup that we set up on ice.
Okay, wow, terrific.
And then I decided I wanted to get into the business side of energy and technology. So I went and got a graduate degree, and then I worked in a number of different business areas dealing with energy and technology. I ran one of the commodity trading businesses, which was how do you buy and sell metals and energy, oil and gas and power and emissions and things like that, gold and silver, and understanding how those sort of things move around is extremely technical, obviously, when you're trying to deal with power, because power is hard to store. A longer conversation on that, but and then dealing with the energy and the tech sector in terms of investments. So I kind of went into the business area. A lot of people I dealt with, it was a very technical area, because if you want to invest money into a new hydrogen fuel cell technology, new wind turbines. I'm a bit older, so a lot of the wind technologies that you see here today, I was involved with at an early stage. Sure. In terms of investing in those solar, so many different types of technologies. And then I was asked a couple of administrations ago to sit on an oversight board at an advisory board at the Department of Energy. So I was appointed by a previous secretary because they wanted someone from my background with a technical and a business background in the sector. And so I sat on that advisory board through the last two administrations. Okay. And then when the president was elected, and they were looking for someone who had a mixture of government and technical background as well as a business background, that they asked me to do this.
I mean, I think that's fantastic. And I love that bio. And for the listeners out there, especially the younger folks who are thinking about what you can do in life, chance really does favor the prepared mind. Here's an individual that grew up being a scientist, becoming a physicist, had a stint in the military, was exceptional there, then went into private sector through business acumen, and then got tapped into public service. It just shows you what, and I want to be clear on this, it really shows you what's possible with STEM literacy and some type of science training, which I think is you're a perfect example of that. So another question, you mentioned wind. One of the questions here, one of the He wants to know, what's the future in your mind of wind energy, and can you tell us about these kites that work like wind turbines?
Yeah. So wind in general has, as we would call it, has bent the cost curve.
Mhm. Okay.
When I originally started dealing with wind, there was companies that were building wind farms with just two blades, and the gears, let's say, broke constantly. And I used to drive through Altamont Pass in California, and there was wind turbines all over the place, none of which were spinning because they were all broken.
Wow.
And so, we used to say, this is not a technology that works. And there were lots of bankruptcies, people invested money, but the technology itself was not working. Well, a new generation of people came along and looked at different aero designs for the wind blades. Obviously, the gears, a lot of material science, materials engineering, design, and really pushed the technology. And about 10 years ago, they started getting a bit closer towards being cost effective. And the engineers kept pushing harder, and wind has pros and cons compared to the availability at night, and so on. And energy has different value and different uses. There's pros and cons with different energy types, but the most important thing is that the cost per megawatt hour of these wind turbines now are cost effective at the market without any incentives.
Oh, wow.
Now, and so that was done by engineers and people who studied STEM and said, yeah, the old ones used to break. Let's try to figure out how to do it so it doesn't break. And you want to reach a point. There's a bit of a philosophical point, but you want to reach a point in which you don't need any extra money or incentives from someone. You want to invent something that makes sense under all circumstances, and it makes economic sense, right? And so that's what's happened with wind. It's now economic without any incentives during a lot of the times a day and so on. And so it's a real alternative as a result. There are many engineers out there coming up with other ideas, right? Like some of the ones that the kite ones that you're referring to. That clearly has an advantage that it doesn't use up land space. I mean, some people critique, people have different opinions about whether a wind turbine down the street is an eyesore or it's wonderful.
Sure. Art is in the eye of the beholder.
Yeah, I'll leave. That's a personal opinion, so I'll just stay neutral on that. But obviously, you could put turbines up in the sky. There's probably advantages to that, as I just described. There's probably disadvantages to it because it's harder to do maintenance on them, and it might wear the turbines a bit more.
Sure.
But what's really exciting about all this is younger generations come up. They come up with ideas they hadn't thought of, and do things better than old people, certainly like me, who was involved with, and that's exciting.
That's true. Folks, you're listening to Undersecretary Paul Dabbar, heads up the U.S. Department of Energy. This is COSI Science Festival Digital Edition. We have time for one last question, and it's a great question to close it out. So Undersecretary Dabbar, what is the development in energy generation that you are most excited about? So you talked about wind, you talked about nuclear. Overall, what's the sector, what's the energy development that really...
Yeah, so the one thing that we're, I think, probably most excited about, and it's tough for us because we're the energy department. We like all the above, right?
Sure.
We want to encourage innovation in everything.
You have a family of children. We all have our favorite kid.
Yeah, that's right. Yeah, I could talk about fusion, which is closer than people think, but what I'll talk about, which is, I think, much more near term, which is batteries and storage. A lot of the power gets generated only when the sun shines or only when it's windy. And we talk about cars, right? And whether they could run on a different energy source like storage, right? Like a battery source. Lithium ion chemistry has now reached a point, as everyone can kind of see from, you got an iPhone, you got a lithium ion battery in there, it works. It's not too bad, right? We think that new chemistries of batteries could improve upon lithium ion 300 to 500%.
Wow.
So hey, lithium ion is great. It kind of works, but imagine, I'll take a car for an example. Rather than 250 miles of charge, imagine it's 1,000 miles of charge. Now the same distance that you have from, or even better than a gasoline engine, you might be able to get out of electricity, right? With that. And we might be able to drive down costs by the inverse amount. So we might be able to have a 75% cut in cost for batteries than the current lithium ion. Those are realistic targets. Now, when you're dealing with science, you can't promise anything. But we see chemistries and people working in labs that said a sulfur-based battery or a magnesium-based battery rather than lithium might be able to have those sort of performance metrics on some of the multiple performance metrics for batteries. And so that is like now, right? There are people now working on that. And if we could jump to that, that would have big impact in the power sector. It would have impact on your electronics, how much stuff you could carry around with you. That's a power hog now that you couldn't carry around, and also transportation.
That's fantastic. That's a great place to end. You just heard it here. Again, we're listening to the Undersecretary Paul Dabbar, heads up the Department of Energy. He just told us, without putting a date out there, so we're not putting you on the spot, but he just told us soon batteries and energy storage will be able to be up to 75% cheaper, but up to 300% more efficient. This is incredible. Sign me up. I will be your first customer. Happy to serve. Ladies and gentlemen, thanks for listening to another great digital session on COSI Science Festival. Please visit #COSI Science Fest, especially tomorrow, to upload your science videos or your great content as we celebrate tomorrow, which is the last day. It's the at-home science celebration. Go to COSISciFest.org. All the stuff you need to know about the Science Festival. Thank you so much, Undersecretary Dabbar, for being with us and really extolling the excitement around the energy sector and how it's going to be great for this country to move forward. Thank you so much for joining us.
Great to talk with you again. Thank you.
Absolutely. We'll have you here in person next time. Take care now.
Thanks.